Welcome to this video presentation on Output 5.3 from the Solarize project. This presentation is about the Living Lab pilot at the University of Portsmouth. My name is Victor Becerra and I am a professor at the School of Energy and Electronic Engineering at the University of Portsmouth. Here are the contents of my presentation. To start with, I will provide you with an overview of the Solarize project. Then I will discuss Living Labs in general, and I will introduce the Solar Living Lab at Portsmouth. I will describe its components and what we measure from it. Then I will provide examples on system monitoring data from the Living Lab. I will discuss some research on modeling the system. And finally, I will discuss weather monitoring that has been performed at the university and how that correlates with the measurements from the Living Lab. Solarize is a research and innovation project funded by Interreg 2Cs and the European Regional Development Fund. The total project budget is about €4 million. There are 12 partners in Solarize, which are located in 4 different countries: England, France, Belgium and the Netherlands. In addition, there are 14 observer partners. The project is led by the University of Picardy Jules Verne in France. There are 3 universities, 1 energy retailer, 7 local councils and 1 smart energy organization in the consortium. The main objective of Solarize is to stimulate, broaden and accelerate solar energy adoption throughout the 2Cs region of Northern Europe. And this is done by identifying and overcoming barriers, by using technology such as smart grids, energy storage, Internet of Things, as well as energy management systems, by proposing cost-effective and affordable solutions that can be adopted, by implementing innovative living labs and a series of demonstrations in public buildings and in households with low-income families, and by delivering training tools and energy roadmaps. Living labs are defined as user-centered, open innovation spaces which are based on a systematic user co-creation approach that integrates research and innovation processes in real-life settings. The key stakeholders of a university-based living lab are academic staff, researchers, students, as well as external partners. Living labs provide the opportunity for staff and students to build solutions that directly address immediate real-world problems and to analyze the behavior of real systems as they operate. Then I'm going to describe the Solar Living Lab at the University of Portsmouth. So as part of Solarize, a Solar Living Lab has been created consisting of installations of 2 buildings of the university. First, the Port Eco House, which is a research facility consisting of an instrumented 3-bedroom household that is used for research in energy efficiency and building performance. Secondly, we have the Future Technology Centre building, which is a £12 million facility that was opened in 2018. And this building is intended for project-based learning and innovation in engineering and product design. In the first location, the Eco House, the following items were installed. We have 15 photovoltaic modules that you can see in the picture, so this type of module. They are fully monitored and in total their peak power is 5 kilowatts. Also 15 module optimizers, which are not shown here in the pictures, but they operate with each of the modules to optimize their operation. A 5 kilowatt inverter was also installed inside the house to convert the DC electricity from the solar array into AC electricity for the house. Additionally, one Tesla Powerwall 2 battery was installed with a capacity of 13.5 kilowatt hours. This battery is able to store energy from the solar panels and for later use. And finally, the installation also involved a Tesla backup gateway, which interfaces with the Tesla battery and the rest of the system. The major installation work was completed on the 7th of May 2021. In the second building, a 40 kilowatt hour Tesla battery storage system was installed and connected to the three-phase electricity system of the Future Technology Center, which is shown in the picture here. This is intended to work together with the existing rooftop solar panels and photovoltaic windows that you can see in the picture. This installation, both at the Future Technology Center and the Eco House, is complemented by a range of equipment that has been purchased to support undergraduate and postgraduate student projects relating to solar energy. Next, I will provide examples of the kind of data that we can acquire from the system that has been installed. In the picture, you can see the total energy production per module from the 7th of May 2021 to the 28th of October 2021. You can see that there are differences between the modules, and these differences occur due to the varying shading that takes place during the day because of different structures that are around the panels, including the wall that you see in the picture, and there is a large building on the left hand side. The bar chart that you see on the right shows the production of photovoltaic energy per month since the installation of the facility on the 7th of May 2021. The normal demand of the Eco House is around 300 kilowatt hours per month, so it is at this level approximately. This demand is typical for a household of this size, 3 bedrooms. With the help of the Tesla battery, the Eco House is self-sufficient for several months of the year. The battery helps store the excess energy generated by the panels above the demand of the household at a given point in time. And then it is able to use it when there is a deficit of solar generated energy. So avoiding as much as possible the import of electricity from the grid. The figure shows the power flows at the Eco House on the 17th of July 2021. Here, the blue curve is the power generated by the solar array. The orange curve is the demand from the house. The yellow curve is the power to or from the battery. And the magenta curve is the import or export of energy from the grid. We can see here how the excess solar power is stored in the battery between approximately 8 a.m. and 1 p.m. This is this yellow curve going negative, meaning that the battery is being charged. At around 1 p.m., the battery becomes fully charged and the excess solar power is exported into the local grid. So you can see that the purple curve goes negative. So it is no longer possible to store the solar energy, and then it becomes exported energy at that point. Also notice that during this day, the house was electrically self-sufficient, with no electrical energy being imported at all from the grid. This happens in particular during the summer months, when there is plenty of solar energy that is being generated. This figure shows monitoring data from the Future Technology Center building. It shows power flows at this building on the 5th of June 2021. You can see how the excess solar power is stored in the battery between approximately 10 a.m. and 17:20 in the afternoon. You can tell that because the solar generation, which is the blue curve, goes above the demand which is the orange curve. That energy is excess energy and it becomes stored in the battery. As you can see here, the yellow curve goes negative. At around 1720, the battery bank reaches a maximum state of charge of 83%. And it then starts to supply the energy to the building until it fully discharges at around 22 hours. You should note that between about 10 a.m. and 22 hours, the power import from the grid was essentially zero. This means that the whole building was running on the combination of solar energy and energy from the battery. Also note that between 2050 and 22 hours, the battery bank alone was supplying 100% of the power demand of the whole building. This data is a good illustration of how battery storage working in conjunction with solar photovoltaics can help maximize the self-consumption of solar energy. Now I will show you some of the research that we are doing with this. So given that we have a system, we can model it using specialist software for modeling photovoltaic systems with battery storage. You can see that we're modeling here the house, the wall, the solar array, as well as the Dennis Yama building, which is on the left hand side. With the model, once we introduce all the details of all the components and the location as well as the demand, the electricity demand, the model is able to predict the production of solar energy from the photovoltaic array. We can then compare the production of solar energy that is predicted by the model with the actual production that is measured by the system. And here we show an illustration of that comparison. So for example, in the case of June 2021, the model is predicting a total generation of 517 kilowatt hours, whereas the measured production was 440 kilowatt hours. Same order, not too different. In July, the model was predicting 505 kilowatt hours, and the actual measured production was 500 kilowatt hours. In August, the model predicted 449.9 kilowatt hours, while the actual production was higher than that at 495 kilowatt hours, and so on. So you can see that with the model we have a good mechanism for predicting solar production. It's not exact, and the differences emerge because the model uses past historical weather data to predict the production, whereas the measurements simply are influenced by the actual weather in those months in the year 2021. Another important thing to show here is these figures that are at the bottom right. This indicates that the total import and export of energy are predicted to be almost balanced over the year. This implies that the Port Eco House has become essentially self-sufficient over the year. It is predicted to generate most of its demand without using a great deal of electricity from the external grid. And if any import is done, it is compensated for by the export that is performed during the year. Another benefit of modeling is that it allows us to predict where the losses in the system occur. None of these components is perfect. They will all have energy losses. And this model allows us to see where the actual losses are occurring. At the University of Portsmouth, there is an existing weather station that is installed at the Dennis Yama building on the roof. This allows logging meteorological data that can support the research and training at the Solar Living Lab. Some of the measured meteorological variables can be very useful for modeling purposes and for correlating with various photovoltaic system variables. The weather station is located within 20 meters from the Port Eco House and within 200 meters from the Future Technology Center building. And this slide shows us an example of the weather monitoring from that weather station and how that correlates with a variable that we can measure at the living lab. On the left-hand side, you can see the mean solar radiation that is measured by the weather station located at the roof of the building. You can see that that mean solar radiation reaches around 1000 watts per square meter. And this is for the month of June, which is summer. Some days will be more sunny than others, as you can see here. For example, days around the 17th and 18th of June are very cloudy, and therefore not much sun was falling onto the sensor of the weather station. On the right hand side, we have the power measured at the AC side of the inverter during the month of June 2021 as well. Here you can see that the two curves, the left and the right curves, even though they are different variables, they are very similar in shape. And the reason is, of course, that the energy that is generated by the solar panels depends on the solar radiation that occurs in real time. And therefore, when there is a lot of sun, there is a lot of energy that is generated by the panels. But on the other hand, when there is very little sun, then of course the panels generate less. And in that way you can see that the two curves are highly correlated. This kind of correlation helps as well with the modeling that can be performed using the data from the living lab. And the data from the weather station, of course, augments what can be done in terms of modeling, because environmental variables are important for the production of solar energy. And this includes, for example, the solar radiation, but also things like temperature and wind speed. With this, I finish this presentation, and I thank you for your attention.